PCM Academy. We are in a lecture series of quantum mechanics, and the mathematical tools of quantum mechanics I have discussed little bit. Actually, we have discussed the property of Hilbert space, because our wave function psi lives in Hilbert space. So, today we will discuss another more important property of Hilbert space, that is the orthonormal condition. In the last class, I have discussed about scalar product basically, and you know, if we have some wave function that is psi, phi and chi, suppose these are some wave function psi, phi and chi, then we have discussed the scalar product of any two vectors. Suppose the scalar product of psi and phi we have defined in this way. So, this is the definition of scalar product, that is equal to basically minus infinity to plus infinity psi star phi dx. Otherwise, if you want to define this scalar product in this way, that is phi with psi, then this will also be defined, that will be minus infinity to plus infinity, in that case phi star psi dx. And here psi star and phi star actually basically the complex conjugate of that function. Okay. So, this is basically the scalar product, and not only this, the scalar product is also defined for a vector itself also. Suppose you have psi with psi, then this scalar product can be defined at minus infinity to plus infinity psi star psi dx, that is basically mod psi square dx, you can see. This is basically mod psi square dx. Similarly, if we have phi with phi, then this is also we can write minus infinity to plus infinity phi star phi dx, and that is basically mod phi square dx minus infinity to plus infinity. This is the basic property of complex number, you know, z star is equal to mod z square. So, these kinds of things we have already discussed. But if scalar product of a wave function with itself gives the result unity, if this is 1 suppose, or this is 1 suppose, then this is called actually the normalized wave function. So, these conditions are actually what? Normalized condition. Normalized condition. So, in that respect, you can tell that psi and phi are normalized wave function, because for psi this is also hold, for phi this is also hold. So, this is the orthonormal, so this is the normalized condition. But if the scalar product psi with phi, suppose the scalar product psi with phi give you null result, that is minus infinity to plus infinity psi star phi dx equal to 0, or if you have phi with psi will give you 0, then in that case you can say that phi and psi are orthogonal to each other. So, this is the orthogonal condition. This is actually orthogonal condition. Okay. So, you can write that suppose two wave function, one is phi I and another is phi j, and the scalar product of phi I and phi j, this can give you the result 1, something like this, normalized condition, or it may be give you the result 0 also. When we can get the result 1, you can see phi with phi or psi with psi, that means when I is equal to j, you can say. So, when I is equal to j, we can get phi I with phi j, that is 1, but when I not equal to j, when phi with psi or psi with phi, you can see 0. So, this condition will hold good for I not equal to j. So, in general we can say this about the scalar product, maybe it is 1 or it is 0. When it will be 1, when the two wave functions are same, and when it will be different, when the two wave functions are different, then it will be 0. So, this is the orthogonal condition and this is the normalized condition, and together we can say this is orthonormal condition. Orthonormal condition. Okay. So, this is basically delta ij, you know. So, we can write it in this way. Now, you can see. So, what we have? If we have two wave function, that is one is phi I and another is phi j, and if you take the scalar product of this, then it will be delta ij. You know, this is the Kronecker delta, and you know that delta ij is equal to 1 if I is equal to j, and this will be 0 if I not equal to j. And this is not hold good for phi also, this can hold for any two wave function, something like psi I psi j we can define in this way also. So, this will also can be delta ij. If this happens, then we tell it as orthonormal, they are orthonormal to each other. They are orthonormal to each other. Okay. So, this is a very important property of Hilbert space. Now, let us take one example such that you can understand this property. Okay. Suppose we have two wave function psi 1 and psi 2, and we have to find the condition for orthonormality. Okay. Suppose we have two wave function. One wave function is, let me take as psi 1. Okay. So, this is our example. Okay. So, let us take psi 1 first. So, let us take psi 1 as a1 phi 1 plus a2 phi 2. Okay. And another wave function, let us take psi 2, that is b1 phi 1 b2 phi 2. So, suppose these are two wave functions we have. What you have to find? You have to find the orthonormal condition. Find the orthonormal condition such that phi I and phi j, phi I with phi j, the scalar product is delta j. This is given obviously. So, in that case, you have to find the normalization condition for psi 1 and psi 2. So, if psi 1 and psi 2 are orthonormal, then what are the conditions? So, what are the conditions that we can get from this information that orthonormal? If psi 1 and psi 2 are orthonormal, then obviously they will be normal to each other, they will be orthogonal to each other, and they will be normal to itself. So, for psi 1 we will get this condition also, psi 1 with psi 1 equal to 1, that is the orthonormal, this is the normal condition, and also we will get psi 2 with psi 2, this will also be 1. So, we will get these two conditions first. Not only this, we will get these conditions also, that is psi 1 with psi 2, this will be 0 because this is the orthogonal condition. Similarly, psi 2 with psi 1, this will also be 0 because this is also the orthogonal condition. So, these are the orthogonal condition and these are the normalization condition. So, when this will happen together simultaneously, then we can say this psi 1 and psi 2 are orthonormal to each other. So, we have to find out that condition just. So, we will use these four equations with this given condition, given wave function. We will operate and we will find the condition, that is the relation between basically a1 a2 and b1 b2. Okay. So, first let me operate this property. Okay. So, psi 1 with psi 1. So, what is psi 1? You have, so whenever you will write psi 1 in this way, this is the bra vector and another one is ket vector. So, if you talk about the bra vector, so this psi 1 will be a1 phi 1 plus a2 phi 2, and if you talk about ket vector, then this will be this. So, this phi 1 and phi 2 will also be ket vector. So, a1 phi 1 plus a2 phi 2. Now, if you multiply with this, that means psi 1 with psi 1, then what will happen? Whenever you multiply this with this, so a1 square you will get a1 square, but this phi 1 with phi 1, so it will be just, you can see phi 1 with phi 1. So, a1 square phi 1 with phi 1 plus you can see a1 a2 and this phi 1 with phi 2 plus you can write that a2 a1 phi 2 with phi 1, okay, plus you will get a2 square phi 2 with phi 2. Okay. So, this will be psi 1 with psi, this is scalar product. Now, you know we have phi I phi j is equal to del ij. So, when I is equal to j, so phi 1 with phi 1 will be 1. So, this will be 1, this will be phi 1 with phi 2, that I not equal to j, that means 0, this is also 0 and this is also equal to 1. So, what you will get just a1 square plus a2 square. and that will obviously be equal to 1, as this is the normalized condition, because this vector, these two vectors are orthonormal. So, normalized condition also will also hold. So, one condition is nothing but a1 square plus a2 square is equal to 1. So, similarly, if you multiply psi 2 with psi 2, then what you will get? b1 square plus b2. So, from here you will get b1 square plus b2 square equal to 1. So, you will get two conditions from these two equations, and we will get another two conditions for the orthogonal condition. Okay. So, let me write that also. Okay. So, now you can see we get two conditions. One is a1 square plus a2 square is equal to 1, and another is b1 square plus b2 square is equal to 1. We will get another two conditions. How? If you are at psi 1 with psi 2, that will be equal to 0. Now, what you will get in that case? You have psi 1 and psi 2. So, this a1, if you take psi 1 in this way, let me write it, this is the bra vector. So, it will be a1 phi 1 plus a2 phi 2. Similarly, if you have psi 2, then you will get, in that case you can see these are actually psi 1, these are actually complex conjugate. So, you have to write it this a1 star and a2 star. The previous one we do not need to write, because this is the a1 square, a2 square, a1, a2, it's complex conjugate there actually. So, a1 star a1 is equal to mod a1 square, you can say. So, that is why I have written directly a1 square plus a2 square, b1 square plus b2 square. But here you can see these two are different, not same, because here you can get actually a1 star into a1, that is nothing but mod a1 square, mod a1 square. So, that is simply you can write it a1 square, but here you can't. So, you have to write for bra vector, this is the complex conjugate. So, a1 a2 will be complex number, but this is the but for kth vector psi 2 we will write simply b1 phi 1 plus b2 phi 2. Okay. Now, if you multiply this, that is psi 1 with psi 2, then what you will get? a1 star b1 plus a2 star b2, because other term, the cross term will be 0, because the cross term will be phi 1 with phi 2 and phi 1 with phi 2. So, this will be 0, vanish, because del ij is equal to 0 in that case when I not equal to ij. Similarly, if you write the reverse condition, that is psi 2 with psi 1 equal to 0, this will be 0 actually, psi 2 with psi 1, then what you will get? You will get in that case b1 star a1 plus b2 star a2 is equal to 0. So, these are the four conditions. So, here the question is find the orthonormal condition, and these are the four conditions, these two, a1 square, a2 square, b1 square, b2 square, and the third condition is a1 star b1 plus a2 star b2 equal to 0, and the fourth condition is b1 star a1 plus b2 star a2 equal to 0. So, these are the four conditions for this problem. So, this is how you can check the orthonormal condition, and this condition, this is orthonormal condition and the orthogonal conditions will be very useful